Hey, Hilo, what's your middle name?
Integrity.
Integrity? What does that mean?
Integrity implies trustworthiness and incorruptibility to a degree that one is incapable of being false to a trust, responsibility, or pledge.
Excellent. Okay. Okay, we're back again, and this is beginning to remind me of the old Dunkin' Donuts commercials where he's going in and out the door, getting up at 3 a.m., time to make the donuts, time to make the donuts. If you remember that old commercial, I mean, he gets up, he no sooner gets done, and he has to go back and keep making the donuts. And at the end of the commercial, he meets himself coming out of the door while he's going in the door. And let me tell you something, this video stuff is getting to be a hard taskmaster, that's for sure. It seems like we no sooner get one done, and you got to do another one. So this is the gun that I ask everybody to comment vote on, and it overwhelmingly is 6GT. And since we did that, here it is. It is indeed, I finished chambering it. I guess I should have had this off of here. Watch. Okay, all right, so there it is. Trust me, it's a 6GT. But that's why that I decided that we needed to do this video, because stuff came up here that is pertinent to things I'm always talking about. Vicki, come around the other side. Oh, and by the way, this is already spoken for. A gentleman decided he wanted it, and he's already taken care of that. So it is already going to be a customer gun. So I chambered this yesterday, threaded, chambered it. I chambered it yesterday, did everything, and I want to show you something. I want to show you how this turned out. So this is a 6GT with a 270 neck in it for 109 grain burgers. Okay, this is for alpha brass. So Vicki, it's going to be hard to show them, but come over here. I want them to see this. All right, watch this. Are you focused as best you can?
Yes.
Okay, watch this. Watch this. Did you see that? Okay. It fits, and that's just one piece of brass. Here, watch. I got 3 different pieces of brass here. Watch. Come back over. Watch this. Do you see it pushing the air out? Did you see the air coming out of the air is coming out of the primer pocket. There's oil in there. Come over here again, because this is the whole point. Watch. Now I'm going to try to move it. And there is, I mean, it's very hard to tell, but on that piece of brass, maybe 1 thou radially. Here, another one. Come in here. Another one. Okay, watch. Watch. That one, watch this. 0. There's nothing on that one. All right, so I was just about ready to put the receiver on it permanently, because you put it on and off a million times while you're building the gun. But I was just about ready to put the receiver on it. And I do this as routine. When I'm completely done, the last thing I do before I put the receiver on is I try the brass, the actual brass that is chambered for the gun. And then here's the headspace gauge. I put the headspace gauge in it, put the receiver back on it, put the bolt in it, and check everything one last time. Now, I've already done that over in the lathe dozens of times, right? But when I did this, it is so perfect that I figured, okay, this is a good opportunity to talk about minimum spec chambers, because the average guy doesn't understand even what I'm talking about. But it's very easy to see. If you see it, I don't have to explain it. Come and watch this again. Watch this piece of brass. Okay? Now watch. I mean, you can barely move that piece. Here, I don't know whether that was the third one or the last one. Where's the one? Right there. Right there. Now, all right, so let me try to explain it, right? What you have here is you have a minimum spec reamer. that was made to this brass. This is alpha brass, right? It's made to this brass, to that bullet. So now you use that reamer to cut this chamber. And then you end up with a chamber that just barely, watch, again, just barely accepts that piece of brass. If the brass was 1 thou bigger, it probably, maybe 1.5 thou, it wouldn't go in the gun, okay? It would not go in. And so the idea of this is you put a high quality piece of brass that's uniform. See, this is the thing. We're at a place now to be able to, okay, let's, again, this is difficult to explain. To be able to work at this level, you have to have uniform brass, very high quality brass. Because the whole idea of SAME spec is that you have tolerances. And the tolerances are actually fairly sloppy. And it makes sense for some things, say like a 30-06. You know, you're building a 30-06 Springfield. If you look on Midway, the last time I looked, I think there's like 150 different loaded ammunition, different types, different bullet weights, different manufacturers, 150 for 30-06. And so the chance that they're all going to be perfectly uniform is like 0. The chance is 0 of that. So you have some that are big, you have some that are small. And so what SAME spec does is it takes all of those tolerances into consideration, and then a SAME spec reamer would accept all of them, which, by the way, is absolutely fine. Say you need a 30-06 and you're going to go hunt the dang world with it, and you're going to shoot factory ammo. Well, having a chamber that accepts all of it can actually be pretty good. And we're assuming that if it's your 30-06, it's not going to need to shoot 1/4 inch. If it shoots 1/2 inch, it shoots 3/4 inch, that'll probably be good enough, right? All right. But when you get into guns like this 6GT bench gun, with this guy, he's already told me he wants to try shooting 1,000-yard with it over at the Missoula Deep Creek range. If you're going to try to win and or set records, your reamer, your brass, your dummy rounds, that's a piece of brass with the bullet in it, have to match your reamer, your dummy rounds, and your chamber all have to match. And the only way you can do that and run minimum spec is you have to have very high quality brass. The higher the quality brass, the tighter dimensions that you can run, because there will be less variation in your components, okay? All right, so you come on over here, okay? So you build this minimum spec chamber, right? And this piece of brass fits in there as perfectly as it could possibly fit, right? If there was any deviation, it wouldn't go. Now, again, the only way you can do that is with super high quality brass, because the uniformity has to be in the brass, otherwise some of them won't go in the chamber. All right, but that's only part of it, okay? Come back over here so that they can understand. All right, you have to think about this. When you put a loaded round in here, and this round goes off, the brass is going to do everything it can to expand, right? Because it's got 65,000 PSI pushing out on it. The powder is going to burn, create that gas, push outward. It has nowhere to go radially, okay? But we'll come back to that. It has nowhere to go radially. So the brass cannot expand beyond its normal limit to spring back, okay? Because people will say, okay, if there's no room, how's it going to expand? So I guess I better address that right now, because people don't understand this. See this piece of steel? This piece of steel is going to expand. All right? That's how strain gauges work. If you put a strain gauge on the side of a barrel, basically what it's measuring is the amount of stretch, and none of this is precise, this is layman talk. It's going to measure the amount of stretch in the steel. How much did the steel expand and then it snapped back, right? All right, so if you have a minimum spec chamber and you put a very strong, uniform piece and pieces of brass in there, when it goes off, it will expand, but it'll only expand to the limit of the actual steel. All right, there won't be slop in there. There won't be 2, 3, 4 thousandths or more slop radially or longitudinally, okay? Because the brass fits the chamber. There's nowhere for it to go. It's already touching the chamber walls the whole way around. So the only expansion that you're getting is in the actual expansion of the steel. And the thing about this is a whole other subject, but I used to build tons of guns. Okay. There are tons of factory guns built on 1.200 breeches. That's not a lot of steel, especially if it's a big cartridge, right? A big Magnum, say 300 RUM. That's not a lot of steel. And so that steel, when that cartridge goes off, is going to expand way more than what we have here. Okay, so, and then I built lots of guns on inch 250. They shot like crazy. But the normal issue with that is, especially say it's a 7 mag, you're only going to get 2, 3, 4, 5, 6 reloadings out of that piece of brass, because even in a minimum spec chamber, there was still enough stretch that it work hardened the brass and eventually it wears out and or separates. This barrel right here, this barrel is, I forget, wasn't this was...
Inch 340?
Yes, this barrel is inch 340, show them. This is inch 340 at the breech, right? So that's a whole lot of metal. Now, here's another component of that. So this is a bat VR. See how much steel there is there? There's a lot of steel, and it is really good steel, and it is really hard, okay? My threads, I mean, it's difficult to even put this on here. Okay, look. Okay? There's literally, there's a little bit of end slop, but this way, 0, and this way, 0. So when the cartridge goes off, even if it is trying to expand the actual steel of the barrel, because the threads are so close, it now also encounters the resistance of the receiver, which, by the way, is significant. Okay, that's one of the reasons why to use certain receivers. This bat receiver has a whole lot of steel in it, and it is very strong. Again, this is 17.4, and it is melanited. All right, so, and my threads are as close as they can possibly be and still function, because I don't want it so close that you have to like crank it on there, because then you start getting interference issues. But they're about as close as it can possibly be and have this thing go on. But okay, so what I'm trying to explain is minimum spec chamber, high quality brass, everything matches. So you put this in here, it builds the pressure, it tries to expand radially, really can't. I mean, it's going to a little bit, because again, it's 30 tons of pressure. It is going to a little bit, but it won't exceed the elasticity or plasticity, I always get those two confused, of the brass. In other words, it won't go beyond the point where it can snap right back. So you put it in the gun, you shoot it, okay? And I've tried to explain this 100 times. Take it back out. You fired it. It comes back out. It comes back out easy. One of the reasons why it comes back out easy is because it never surpassed its ability to spring back. So it expanded slightly. It went right back almost to its identical original dimensions, and it comes right back out of the gun. Okay, now, depending on your neck dimensions, which is like almost a separate conversation, this has a 270 neck in it. So you have to know what your loaded round is. But for the sake of this conversation, let's just say that the loaded, with a bullet in it, the loaded neck diameter was 0.0269, 1 thou clearance. That is only half a thousandths on a side. So what happens is the case cannot expand radially. It really, again, that's another reason for good shoulders and stuff. It's going to try to expand a little bit forward. I should stop and say that. There's kind of like this rule. Anything you do to brass, it's always growing. So like if you pick it up and hold it in your hand, it's growing. Not really, but that's kind of the way brass is. Anything you do to it, it is always growing longer, because the brass has to flow some direction, and if it can't go radially, it only has forward to go. But let's leave that out of the conversation for the moment. Let's say you have a 269 neck, loaded neck diameter. You have a 270 neck diameter in the gun. All right. The firing pin hits, lights the powder, creates high volume of gas that expands rapidly, creates a lot of pressure. The case comes against a minimum spec chamber, but it encounters a lot of resistance because you have a whole lot of steel and you have a really good receiver. Okay, the pressure has nowhere to go but forward, so it pushes the bullet up the barrel. Now, the neck has to expand slightly to release the bullet, because if it didn't release the bullet, you basically have a bomb, because where's the pressure going to go? It has to go somewhere, right? All right, so it has to expand, but like this, just instantaneous. It has to release the bullet. The bullet starts on its way up the barrel. You go to take the case back out. It comes out easily because it never exceeded its ability to snap back. All right. You can take a dedicated, not a normal set of RCBS dies, a dedicated decapping pin. Some guys, bench rest guys, use a hand one. They just pop out the primer, right? Put it on there, a pin comes through it, pops out the primer. Boop, pop out the primer. Okay. You can wipe your neck off with a piece of steel wool or something to get the little bit of carbon off of it. Put a new primer back in. This is the part guys don't understand. Don't do anything. Do not let a die touch this, all right? Put your powder back in, seat a bullet on top of there, put it in your bullet seater, which it's a die, but it's not touching the case. Make sure your bullet seater doesn't touch the case. Seat the bullet back, and you'll still have the same neck tension that you had when it was brand new, because it is brand new essentially again. It's once fired, but it has gone back to the as new dimensions, okay? Seat a bullet, put it back in the gun. Now, when you go to put it back in the gun, you want to feel what type of bolt closure you have, right? Because brass is always going to work hard, and it's inevitable a little bit. But in this scenario right here, with these dimensions, these minimum spec dimensions, in all likelihood, you can just put it right back in the gun, close the bolt, and shoot it. And by the way, I will digress here just for a second. The one thing about bolt closure resistance is uniformity is 1,000,000 times more important than ease of closure or difficulty of closure. That's not what's most important. What's most important is that the bolt closes the same every time, all right? And ideally, in this situation, it'll probably go right back in, and the bolt will close exactly the same as it closed when the brass was brand new. So you didn't do anything to it, and okay? And I always skip this part. What is the advantage to that? Well, if you had perfect brass, let's just say, which some of the brass is getting so high quality now, I mean, it's amazing. They are doing excellent jobs, some of these companies. ADG, Alpha, Lapua, Peterson, I mean, we're getting some really good brass. But I've been doing this for years. I've never saw perfect brass. If you had perfect brass, all of this stuff I'm talking about in some ways would be irrelevant. It really wouldn't matter, okay? If you had perfect brass, everything would be uniform. It would just push all the bullets through the exact same hole, punch them right through the same hole. But because brass isn't perfect, firing it in your chamber, and we're hoping here, we're assuming, if someone really did a good job, that the chamber should be more perfect than the brass. In other words, because the chamber is one thing. The piece of brass, you have 50 pieces of brass. They're all individuals. They may have come through the exact same set of dies down the exact same line, or they may not have. They may have come from two sets. Okay, again, that's too deep to go into here. But the chamber is one thing that hopefully is perfect. All right, if the guy building the gun did everything properly, we're going to assume that the chamber is the most perfect variable out of all these variables. Okay, so you took your nearly perfect brass, you fired it in your perfect chamber. Well, they were all subjected to 65,000 psi. It would be incorrect to say that you ironed out the imperfections. That would not be technically accurate. I remember in Tony Boyer's book, he said he never goes to a big match unless brass is fired 3 times. 3 times from Tony Boyer. If you don't know who Tony Boyer is, you need to look this up. The most winning bench press shooter in the history of the world. Nobody else is even close. And he said big matches, 3 times fired brass. The thought is that even though it's not eliminating the imperfections in the brass, putting it in a perfect chamber, a uniform perfect chamber, and firing your almost perfect brass, God, this is difficult, irons out some of the imperfection. Some of the imperfection. And what I'm trying to say is, assuming you have a really great chamber, the brass coming out of the chamber should be better than the brass you put in it. And the only way it wouldn't be is if you had perfect brass. Again, I said, I never saw perfect brass. I see some pretty good stuff lately. But if you don't do anything to it then, in other words, you don't touch it with a die, because people, you might spend $100 on a set of dies. You might spend Reading Type S match dies now are like over $300. You might buy custom dies for $1,000. There's no guarantee that the die isn't introducing irregularities back into the brass. So again, I realize this is super confusing, but so you have brass. We're going to assume that the brass isn't perfect. We're going to put that brass in the chamber. We're going to fire it, and then we're going to assume that the brass that came out of the chamber is better than the brass we put in it. Now, why would you want to put it in the die? You know what I'm saying? Why on earth would you want to possibly run it in a die and possibly introduce air into the thing? If you can just take it out, knock out the primer, don't do anything to it. Don't even touch the neck with a bushing. Put another bullet in it, put it back in the gun, and the only thing I would do there is sort them by bolt closure. Like I'm saying, if the bolt closure is uniform, then shoot them. Shoot them. And if you have a bench gun, it's going to be very easy to see on the paper whether you gained accuracy or whether you lost accuracy. And that's how you can test your dies too, by the way. Say you had a custom full-length sizer die. Shoot new brass and see what the groups are. Shoot once fired resized brass, see what the groups are. And then you know whether your die is helping or whether it's hurting. All right, so come back over here so that we can see what we're doing here. Sorry. That's the whole idea of minimum spec chambers. Minimum spec chambers are not for the average guy, first of all. And if it's going to be a hunting gun that's a 1, 2, 3, 400 yard hunting gun, in other words, not a long range precision hunting gun, you may not want true minimum spec. But if you're competing in bench rest, if you're competing in 600 yard, you're competing in 1,000 yard bench rest, or even PRS, having the relationship, come over here, between your reamer, between your brass, that is your dummy rounds, including the bullet, because the reamer also cuts the throat for whatever bullet you're going to be using. But having the relationship between the reamer, the brass, and the chamber as close to possible, which we just say minimum spec. I mean, we just say minimum spec, not SAMI spec. Having them all as close to minimum spec as possible and matching each other is a great advantage. It is a great advantage. That's how you win. I mean, you want all the bullets to go through the same hole. You have to address all of these things. And so if you want your bullets to go through all the same hole, start with the highest quality brass you can find. Start with the highest quality bullets you can find. In bench rest, those are custom-made bullets, right? But start with the highest quality bullet that you can find. Make dummy rounds out of those combination. Send those dummy rounds now to Ray Gross, who's the main man now at Manson Reamers. Send them to Ray Gross, and you say, Ray, I want you to make me a reamer to exactly match my dummy rounds, but with enough clearance, look, again, with enough clearance that it just goes in. Just goes in. And it's literally it's as perfect as it can be. If it was any more perfect, it wouldn't function. And I know there'll be 1,000 guys out there who say, well, if it's that close, what if it, blah, blah, blah. I don't care about all that. What I care about is the bullets going through the same hole. I mean, you're not building a 375 H&H Lion rifle to minimum specs like this. So those arguments don't matter. If it gets dirty, what happens, blah, blah, blah. That doesn't matter. What we're concerned here with is extreme precision, putting all the bullets through the exact same hole. So I think that's it. Oh, I wanted to show you this. We showed it while it was on there. So that's a barrel stub. I doubt you'll be able to see it, but it tells you on the barrel stub, this is a Bartlein. That means it's a 4-groove. This is 236, and put my glasses on. 236, 243. This is a 1 in 8. SS means stainless steel, and that is the actual serial number of the barrel. And here's the muzzle end of this. Okay, this was a 31-inch blank. Again, this is big, 1.1. And again, I have a few little secrets, but this is where I determined to cut it. So the barrel is approximately, I don't know, it's about 27 3/4 inches or 27 7/8, something like that. Again, that kind of stuff doesn't matter unless you're trying to make weight, which in bench rest, there are different weight categories, right? So I think that's it. I am now, when I finish here, I'm going to put this receiver onto this barrel for the last time. And then once it's tight, I will run this brass back in there, check the headspace. I'll put the headspace gauge in there, check that, and if everything's good, then you move on to the next part. And by the way, come back, one last thing. So you realize we always just have one go gauge. All right, the go gauge is fine for getting you close to where you need to be. But whenever I'm actually building a gun of this level, all right, this is a bench gun, I use the actual brass. In other words, and that's one of the reasons why these are here. I should have mentioned that. When we put these in here, these three are not identical. They're varying, they're about maybe half a thou. And so what I do is as I'm coming up on the last, 5,000s, 4,000s, 3,000s, as I'm chambering, I'm using those three different pieces of brass, and I'm running them all in, and I'm closing the bolt on them, and seeing how everything feels until I make my very last 1 or 2 thou. And obviously, all the brass has to go in. But to do that, that's why one of these, you have a little bit more. The brass isn't perfect. So you have to make it, of the three here, you have to make it so that the bigger of the three goes in. And so if that gives you half a thou or 1 thou more headspace on the smaller one, well, that's just the way you have to do it, because the only way you could actually get it perfect is if you chambered to one piece of brass, But then you'd be stuck shooting that single piece of brass, which I just watched Gavin Gear over at Ultimate Reloader. He took one piece of brass and he loaded it, fired it, loaded it. He was annealing it, loaded it, annealed it, fired it, loaded, annealed it, fired it. And I think he got something like 75 firings out of one piece of alpha brass before finally it cracked at the shoulder or at the neck. So you could do that. Or you could do what a lot of bench rest guys do, is they will sort through 100 pieces or 1,000 pieces of brass until they end up with 20 or 50 that are as close to identical as possible. Then they do this same process with them. But again, that's if you're trying to set world records, okay? The point is, you can push this a long ways down the road, and you can go deeper and deeper and deeper until eventually it just drives you nuts and it's time to make the donuts.